Okay, so starting this new unit, new chapter about minerals, kind of lead into that with just a real basic refresher, hopefully, on some chemistry. So for those of you that have had chemistry or ICP or something like that, it should definitely be just a brush up. So matter, this is a vocabulary term we've seen already. Anything that has mass and volume. So anything that is made up of something, it's made up of stuff, and it takes up space, which is pretty much everything that we know of. There's something there, it takes up space. So when you think about it, it all matters because it's all matter.
No pun intended.
Oh, that's where you'd be mistaken. Next one, element. So an element is something that cannot be broken down chemically. So it's already at its most basic, simplest, purest form. It can't be broken down. If you have a compound or something where you have different elements that are joined together, you can break down compounds chemically into the different elements that make up that compound. For example, water, H2O. So you have 2 hydrogens, 1 oxygen. You can break water apart into just pure hydrogen and pure oxygen. You can do that chemically. Now, if you just take the oxygen portion of it, you can't break that down anymore because it's already pure oxygen. Because it's in its elemental form, it's pure. All right. This is just an example of the periodic table. This one happens to show pictures or examples of the different elements, most of which, kind of surprisingly, are metals. Even things that you don't think about being metals, in their elemental form, in their pure form, they are metals. It's just that we're more accustomed to seeing them in some sort of a compound, which makes them not look like metal. Like a great example is sodium. Over here on the left side, sodium metal. And probably the place that we're exposed to sodium the most is in salt, sodium chloride, which looks nothing like a metal, but sodium is a metal. So, like I said, this is just one example of a periodic table. Also, the pictures of people down here, they aren't made out of that element. It's who they're named after, like Einsteinium and Nobelium and things like that. That's why they're there. Right, so the next thing, onto the atom. So first off, everything is made of atoms. It's how it is. Kind of the basic definition is an atom being the smallest part of an element with all the properties of that element. So, if you, using the water example, if you take one atom of that oxygen that you separated from water, it's still oxygen. It still has the same properties of oxygen. You can't break that apart into something smaller and still have it be oxygen. You break it apart, then it's into the pieces that make up atoms, and it's not oxygen anymore. So the atom is just the smallest piece of an element. It's still an element, which is one atom's worth. The main part of any atom is the nucleus, and that's where the vast majority of the atomic mass is. So 99% of it is in the nucleus, and it's the subatomic particles, so the particles that make up atoms, the protons and neutrons are found in the nucleus. because there are 3 subatomic particles: protons, neutrons, and electrons. So sub, the prefix sub, meaning below or under, or kind of what, the smaller parts. So protons and neutrons are in the nucleus, and then electrons move around the nucleus. So the picture that's on this slide, I think, does a decent job of kind of representing more of how an atom really looks compared to some of the other drawings and I guess depiction of an atom that you see or that you're used to seeing. So there's a nucleus in the middle, and then you have these different energy levels. So you have the first, like the inner energy level, and then the outer. Typically in drawings and kind of illustrations of atoms, it looks like the electrons just go around the nucleus like a planet orbiting the sun. And that's not the case. Drawings like that do serve a purpose, which I'll touch on here in a minute, but it's kind of more like this drawing, where the electrons move around the nucleus in more of a cloud. That first energy level, that electrons could be anywhere in that level at any time, but it's not just one path that it just follows and follows and follows and follows. It's not like that. So this one, like I said, I feel like it's a little more accurate as to how the atom is really set up, not to scale or anything like that, which we'll see, but something to think about. All right, so the video, wherever it went. Okay. Oops. All right. So this is just a few minutes long. I'm not going to show the whole thing, but it's kind of crazy to think about stuff like this.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of actually the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? That's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. And that's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the earth, which really are the atoms in the grapefruit.
All right. Cut that a little bit short. But it's kind of crazy to think about. If every atom that was in a grapefruit was suddenly the size of a blueberry, which I mean, is not very big, it would be the size of the earth. Are really small. Okay, so to kind of back that up or expand on that, I guess, there was, and this is one of the kind of key experiments that demonstrated that most of the atom is empty space. Some scientists had they set up this experiment where they had this source of radiation, this alpha particle source. Alpha is just a specific type of radiation. But you can think of this as a laser. So they set it up, they shot this laser at a piece of gold foil, and then around the foil they had material that would detect that specific type of radiation. When they turned the laser on, aimed at the gold foil, they found out that most of it is empty space because the vast majority of the radiation went directly through the gold foil like it wasn't even there. Now there were some that, some bits of radiation that bounced off of the nucleus of some of the gold atoms and, were then dispersed in different areas versus where it was aimed at. But most of the radiation went right through it like it wasn't there. And I mean, this is happening all the time to all of us. I mean, right now, there's radiation going through our bodies, and most of it doesn't touch anything. Aside from radiation from space, radiation from the earth, you think about any sort of, electromagnetic radiation that's in the air, cell phones, microwaves, radio, TV, any of those waves that they're moving through the air are going through us as well, all the time. Like I said, most of it doesn't touch anything. Sometimes that it can, and sometimes it can cause some damage. And typically, radiation isn't a good thing to be around. You don't want to be around it any more than you have to. But even the most solid objects that you can think of, again, most of it's empty space. When atoms interact with one another, the nucleus of the atoms, they never come into contact. The interactions take place between the electrons that surround the nucleus. So those are the things that are actually, and even those aren't coming into contact, but they're what is, like I said, interacting with the other atoms, not the nucleus of one atom and the nucleus of another atom. It's the electrons of the atoms that are kind of forming bonds, and which we'll talk about probably tomorrow. It's not the nucleus, because the nucleus is such a huge distance away that they don't interact. All right, so a little more on the atoms and specifically the nucleus. In the nucleus, that's where the protons live. I say that even though they aren't alive, but that's where you'll find them. Protons have a positive charge. The protons that start with a P have a positive charge, which also starts with a P. All protons are the same, so it doesn't matter if you take a proton from carbon and one from platinum and one from uranium, they're all the same. It's not element specific thing where, oh, this is only, this is only an oxygen proton. They're all the same. And kind of the unit that's set up to measure the size of these subatomic particles is the atomic mass unit. And the proton has an atomic mass unit of 1. So we aren't going to use this unit much at all. But it's something to kind of think about, today as we're talking about this, just to give you an idea of the relative size of these subatomic particles. Also found in the nucleus are the neutrons. The neutrons have no charge, or you could think of it as neutral. So it's not positive, it's not negative, it's neutral. Or if you like cars, it's not in drive, it's not in reverse, it's just in neutral, it's just sitting there. It also has a mass of 1 AMU, 1 atomic mass unit. So the neutron and the proton have the same mass. And both of those are found in the nucleus. So now moving around the nucleus, as we mentioned, is the electron. Electrons have a negative charge. So protons have positive charge, neutrons have no charge or neutral charge, and then electrons have a negative charge. But look at the mass of an electron. So 0.0006 AMU. So that's 6/10,000ths of an AMU. So if you took a proton, chopped it into 10,000 identically sized pieces, took 6 of them, that would be the mass of 1 electron. So as tiny as an atom is, electrons are ridiculously that much smaller. And these things are incredibly, incredibly small. So as I mentioned, they're found in more of an electron cloud versus just an orbit, like this picture shows. And they're found at energy levels. And this is kind of where this type of a drawing or an illustration of an atom is good. So looking at this, you can easily see the energy levels. You can easily see it there too. And you can also see how many electrons are in each energy level, because that's not always the same. The first energy level only holds 2. The second one holds 8. And then as you have more and more for, whatever, depending on which element it is, you'll need a different number of energy shells or energy levels. But this type of drawing is good at showing, how many electrons are in each energy level. So while it's not completely accurate as far as how things really are, it does serve a purpose, and it's good at conveying information pretty quickly. Because you can look at this quickly and say, okay, there are 2 energy levels. There are 2 in the first one, there's 4 in the second one. So there's 6 protons, there are 6 electrons, which moving on to a couple other slides, we'll learn a little more about. So as you look at the periodic table, for some information about each element, probably the most important number is the atomic number. So this is a really, really basic entry for a periodic table. So the abbreviation C for carbon, the atomic number is 6, and that tells us the number of protons. The reason the atomic number is so important is because that's what determines what the element is. If there's an atom and it has 6 protons, it's carbon. You cannot have a carbon atom with anything other than 6 protons. 5, it's boron. If it's 7, it's nitrogen. But in order for it to be carbon, it has to be 6. So whatever the atomic number is, that's what element it is. So it's, like I said, it's an important number. It's an important piece of information. In addition to that, whenever you have one single atom of an element, it has no charge. It's neutral. because you have equal numbers of protons and electrons. So for this example, if you have 6 protons, then you're also going to have 6 electrons. So effectively, the atomic number not only tells us the number of protons in an atom of that element, it also the number of electrons. It is possible for an atom to be charged, but we'll talk about that later. Then the last little piece is the mass number. So that's this bottom number, this 12.011. What the mass number tells us is the mass of the nucleus. So the protons plus the neutrons. So if you add up the number of protons and the number of neutrons, you end up with the mass number. But 12.011 is kind of a strange number to get if you're adding 6 protons, and because I subtracted 6 from 12, 6 neutrons. How do you get this 0.1 or 0.011? You can't have 0.011 of a neutron. It's kind of like saying, and I'm making this up, that the average family in America has 2.3 children or something. You can't have 0.3 of a child. I mean, even if they're short, you can't have 0.3 of a child because it's an average. They're taking all the data and they're averaging it out. This number is an average. It's an average of all the isotopes of that element. So carbon, there are 3 isotopes. There's carbon-12, which is the most common. So you have 6 protons and 6 neutrons. So you would have a mass number of 12. Carbon-13 has 6 protons and 7 neutrons. You have carbon-14, 6 protons and 8 neutrons. Carbon-13 and carbon-14 are not very common at all. We all have some of it in our bodies because it's radioactive. You take it in when you eat things. It's normal. It's also what they use for radiocarbon dating. Have you ever heard that mentioned? Scientists are trying to figure out how old something is that used to be alive. Then they can use carbon dating. They can look at how much of this carbon-14 is left. But this number is the average of the isotopes based on how common they are. So because carbon-12 is much, much, much more common than the other 2, that's why it's almost carbon-12, just barely. This is just barely not carbon-12. So with the isotopes, it's the same proton because it has to be that element, and then different numbers of neutrons. So remember the protons and neutrons in the nucleus. You have electrons orbiting the nucleus or going around the nucleus. The atomic number tells us the number of protons, and in turn the number of electrons. And then the mass number tells us protons plus the neutrons in the nucleus. Are there any slides I need to go back to? Does anybody have any questions?
Can you go back to, oh wait.
To which one?